G'day, Chris here and welcome back to ClickSpring. So with the main jaws of the tool complete, it's time to move on to the hardware that makes them work. And they operate much like many of the other clamps that we might find in the shop, where the jaws are brought down upon the work with a closing screw providing the clamping force, and a height adjustment screw ensures both parallel jaws and takes advantage of the slightly free pivoted movement to ensure a firm grip at the front end of the clamp. It's an idea that pops up repeatedly across various work holding systems. But of course, the clamps in this build have the added requirement that we'd like them to hold their position on a vertical plate for more convenient use. And the way we achieve this is with an internal spring that serves to drive the jaws apart, and so provide a modest closing grip on the main plate to which they're fitted. All of which is to say, we now have a need to create some custom springs for this tool. The date of a spring formation can be found in Machinery's handbook, with the key piece of information being the diameter of the arbor around which the carbon steel wire is to be wound. The process of making a spring on the lathe has much in common with thread cutting. The lead screw is geared to the spindle rotation to give a pitch to the spring much like the pitch of a screw thread. The key difference, of course, is that there's no cutting. The machine is just serving the role of a platform to feed the wire onto the arbor at the chosen pitch. Now there is a tendency for the forces generated as the wire is wound onto the arbor to deflect the whole arrangement off the axis of the lathe, so tailstock support is going to help. And although the actual forming can be done under power, for a small number of turns I generally choose to rotate the spindle by hand. A couple of inactive coils prior to the main set will provide a clean start to the spring when it comes to tidying up the part. Then, much like single point threading, the half nut is engaged with the lead screw and the coils are formed. A couple of inactive coils close off the part, and then it can be separated from the wire stock. Each spring end I'd like to be closed and ground to a flat, and a great way to maintain control over the part while the flat is formed is to pop it onto some rod stock and then hold it in something like this finger plate clamping tool. Now in their present form the springs will fit and do the job just fine. But given that this is a watchmaker's tool, there's an opportunity to practice that mindset generally required when working on high quality horological components. Whether it's a mostly hidden spring like this, or a highly visible component of a watch or clock movement, a part isn't really considered complete until every surface has been given full consideration regarding its final finish. Now this is partly about appearances for sure, but it's also about how that finish serves the component's function and lifespan within the overall mechanism. And it's not always about giving everything a high polish. Sometimes it might be best to just put a straight grain on a part and leave it at that. But generally there's an optimum combination of finishing techniques that best suit the material, what the part needs to perform its function long term, and the aesthetic needs of the overall mechanism. In this case, it's a carbon steel part that needs to experience no binding despite having a lot of contacting surfaces, and I'd like it to remain corrosion free for as long as possible. So I've gone for a high polish to the coils and a black polish finish on each of the ends. This should give occasional glimpses of reflected light from within the body of the tool, and also make sure that the spring action has a slick, high quality feel for many years to come. Now the component over which these springs are intended to operate is what I'm calling the threaded insert. It's a simple part, yet it performs several roles at once. It's the nut that restrains the whole assembly. It's the shaft that provides the primary jaw alignment, and it also acts as a guide for the springs. And as it happens, it's also well suited to being formed with the machine on which it will ultimately be used. The part is designed to move freely within the slots on the main plate formed in part 1 of this build series, with the end narrowed to opposing flats separated by a suitable width. Now it's the column section of this component that provides the primary alignment for the assembly that I mentioned previously, and the remaining alignment comes from the small pin on top of the height adjustment screw. Although none of this is rigidly constrained, we actually need a little bit of free movement in that top jaw for the height adjustment screw to be able to do its thing, which, in addition to ensuring that the jaw faces are parallel, is to provide a limited means of gently biasing the clamping force towards the front end of the jaws when required. And so it needs to be easily manipulated between the fingers while still giving a good solid grip. Now certainly this grip pattern could be made with a straight knurl, a process that mostly deforms the metal into shape. But an alternative is to cut the pattern, using the same tools that are generally used for wheel and pinion cutting. My preference is to cut wheels and pinions on the lathe, using a milling attachment on the cross slide, with the main difference in this case being that the cut profile is a much simpler V-cut, using a fly cutter from a previous project. Now the faceted nature of this part makes it well suited to being a visual feature of the assembly, and with a decent polish it'll stand out nicely in contrast to the otherwise mostly grained surfaces. The length of the thread is something that requires a little care. Ideally, I'd like to maximise the working range of the height adjustment screw, but in its fully closed position, I'd like it to remain just clear of the main plate. And the lower jaw provides a convenient reference for the cut. And now that we have a clearer view of the part, the other features worth mentioning are the small boss on what will be the upper face that acts as a simple bearing surface when the height adjustment screw is engaged with the upper jaw, and also the pin that's a free fit within the matching hole of the top jaw that allows everything to move as required when the clamps are in use. And that brings us to the last components for the clamp assemblies, with both a styled washer and a rope knurled thumb wheel. Each component has a curve in its perimeter, and of course I prefer all three instances of each component to look the same, and in a home shop that's a perfect job for a form tool. For the washer, the primary cut is a simple circular curve. I can position the cut using a length mark and also a depth indicated by a turned boss section on the end. If the cut terminates simultaneously at both, then it's ended up where I need it to be. The cutting tool I'm using is one of the button cutters made for the Tools Glorious Tools Gear Cutter series, and it just happened to be a good size for this project. I'm running the lathe as slow as it'll go, about 100 RPM, and feeding in by hand to keep that chip fairly continuous and chatter free, a bit like running in a parting tool. The washer can then be pressed onto a stub arbor, trimmed to length and brought to a final finish. Okay, so that's the washers sorted, now for the knurled thumb wheels. The perimeter is a little more complex, but again it's well suited to a form tool. If the cutting tool can be shaped well, it'll repeatedly print the same pattern on a brass stock as many times as required. Now, like any cutting tool, it needs relief beneath the cutting edge to cut properly. So after forming a date and face, and the curve required to accept the rope knurl pattern, a compound angle can be set up using both an angle block and the swivel feature of the vise to form the bulk of that relief. What will be the underside curve of the thumb wheel can be manually marked in and then relieved with the belt sander, taking care to avoid touching the rest of the profile with the belt. And the relief of the small curved section I've found easiest to simply cut with a file, again taking care to not alter the profile of the cutting edge. And then it's into the heat treat and quench, using powdered boric acid mixed into a slurry with denatured alcohol to minimise the heat scale. I keep this file reserved solely for this hardness test, listening for that familiar sound of it skating over the surface of a glass hard part. Once that's confirmed, the part can be brightened up on some stones to see the temper colour as it runs up towards the cutting edge. In this case, I'm after a medium straw colour. The cutting edge is most easily brought up on the belt sander. And once mounted in a holder, it's ready for use. And one of the really cool things about this sort of form tool is that it can be repeatedly sharpened simply by giving that top surface a light touch on the same belt sander. Now, to the extent that it's possible, it's usually helpful to minimise the amount of cutting edge engaged by a form tool. And so the blank stock is prepared with a narrowed section, leaving only that length of material at the required outside diameter that actually requires profiling. As for the previous form tool cut, I'm running the lathe at its minimum speed and aiming for as continuous a ribbon of brass as I can generate. And after all of that preparation work, the knurl itself is the fastest and easiest of all of the steps. The tool is brought into contact with the metal with moderate force and permitted to form an initial print. Then, with the machine running at low RPM and for no more than a few dozen turns, with a gentle infeed, the pattern quickly forms to the required depth, leaving the classic rope knurl. I'm using threaded stock for the functional thread of the thumb wheel, and it will also serve as a useful arbor to hold the knurled part while forming the domed feature. And while there are probably more repeatable ways to get that dome onto the part, it's hard to pass up the chance to do some hand turning with the graver to close out this section of the build. Okay, so that's all of the bits and pieces. Let's put it together and see what we've got. So the tool is well on the way to being completed, with the key work holding features in place. And generally, it's common for this tool to have a nickel-plated surface on that main plate. Although that might be a little too bright alongside the Sherline, so I'll give it some more thought before deciding how to best treat it. At the very least, in the next video, I'll make the drawbar and centering features, and also go through how the tool is used in traditional watchmaking. Thanks for watching. I'll see you later.